Awesome. Thanks for reminding me. That was great. Um, so yeah, so now we should be streaming on YouTube. But yeah, so one set arrow diagrams, we just use one set of values like we did here to represent all the relations. And we can do that because the codomain and domain are the same. That's opposed to a two-set arrow diagram. And we do this when the domain and codomain are not the same set. So for like a two-set arrow diagram, we would have the domain on the left side and the codomain on the right side. So we might have something that looks like this, where you have 1, 2, and 3, and then maybe on this side you have 0, 2, and 4, and then you have your arrow relations like this. So you've got one set of values on the left, and then another set of values on the right, and they don't represent the same set of values. So yeah, really good question. Any other questions on arrow diagrams? Awesome. So let's go to this next problem. So this is a problem on relations. So we've got this set S, 1, 2, 3, and then we're going to look at relations over the power set of S, and we're going to decide if this relation is reflexive, antisymmetric, or transitive. And if the property fails, then we're going to give just specific counterexamples. So you don't need to, so if the property is true, you don't need to prove it. But if you believe the property is not true, show a specific counterexample as to why that fails to hold. So if you just want to take 30 seconds to write this down, and then we're going to do some breakout rooms so you can talk to some other people about if you think it's reflexive, antisymmetric, or transitive, and why. And then I'm also going to see if this works to just send the... Yeah, so in the chat should be a PNG file that has the question as well, if you need it. Awesome, so you should be all going to breakout rooms, and then you can talk there. And that looks like we have Austin didn't join. Let me join that. Let me assign you to a breakout room. We're just talking about this problem on relations. And then you can join one of the breakout rooms too if you want to, Lynn, or just hang out here. Awesome. So it looks like we're all back. So hopefully you had enough time to kind of think about that a little bit. So for the first part, so let's see if this relation is reflexive. So any group have any ideas on if the relation is reflexive or not? Oh, did the screen go away? Okay, let me... Oh, what happened? Okay, so is the screen back now? Okay, good. So yeah, so any group have any ideas for if this relation is reflexive or not? If you just want to type in chat if you think it is or isn't. Yes, we have some saying, yeah, not reflexive. And yeah, so Peter gave the answer. You're right, because the intersection of two sets is just the set itself. That's clearly not the empty set. So let's give a specific counterexample. So whenever we want to show that a property is not true, we need to give a specific counterexample that shows it's not true. So let's consider, so we've got the element 1. That's in the power set. And then if we take just the element containing 1, intersected with 1, that equals the set 1. And that's not the empty set. So we don't have, so negative, so the set containing 1 is not related to itself. So it's not reflexive. What about antisymmetric? So let's type in chat if you think this is or isn't antisymmetric. Okay, so we have some people saying that it's symmetric, so it's not antisymmetric. So that's the right idea, but make sure you remember that symmetric and antisymmetric are not opposites of each other. So you can have some relations that are both not antisymmetric and that are not symmetric. So just make sure you remember that they're not just opposites of each other. So make sure when you're saying something's not antisymmetric that you remember that. But yeah, you're right. It's not antisymmetric. And the reason is because, yeah, we can find an example such that if AB is related, then BA is related. Yeah, and Andrew just gave a perfect counterexample. So what they said is if we take the set 1 intersected set containing 2, that equals the empty set. But also, if we take the set 2 intersect with the set 1, that also equals the empty set. So we would have 1, 2, and set containing 2, 1 in R. So it's not antisymmetric. Antisymmetric requires that if AB is in the relation and A is not equal to B, then BA is not in the relation. And we just found a counterexample to that. So it's not antisymmetric. What about transitive? If you just want to type in chat whether or not you think that this relation is a transitive relation. Okay, so we have one person saying not transitive. Anyone else think it's transitive or not transitive? Yeah, so it looks like just the one, yeah, not transitive. So yes, it is correct. It is not transitive. But let's figure out the counterexample as to why. So remember that for transitivity, it requires that um, if AB is an R and BC is an R, then that implies that AC is an element of R for all A and B and C. So we can find an example such that if we take the previous example that we had for antisymmetric, we had that 1 intersect the set containing 2 is the empty set, and the set 2 containing intersect with the set 1 is equal to the empty set. But, so we have, this is A is related to B, B is related to C, but the set containing 1 intersect with the set containing 1 is just the set 1 and not the empty set. So it's not transitive. And then, yeah, so Andrew has another counterexample. So they looked at the set 1 intersect with 2 and 2 intersected with the set containing 1, 3. And that also works perfectly. Yeah, there's definitely several examples to show that this is not a transitive relation. So any questions about this? About any of this reflexive, antisymmetric, or transitive here? Yeah, so someone asked, so not reflexive and symmetric implies that it's not transitive? I'm trying to think if that works always. I don't. That always does not hold. Um, you can certainly have relations that have none of these properties, that are neither reflexive, that are neither transitive, and um, are not transitive. But I can't. Yeah, I would be wary to say that that holds in general. If something's not reflexive and it's not symmetric, that implies it's not transitive. In this case, that holds, but I'd be wary to make that generalized statement. I'd have to think about that a little bit more. But I think you can find an example that is not reflexive, not symmetric, but actually is transitive. Yeah, not reflexive and symmetric. Yeah, I would be wary to say that that holds in general, but I'd have to think about it. Awesome. So let's go ahead. If there's no other questions, let's move on to this next problem. So here we've got this problem on proving some properties of relations. So we're going to prove that if R is a transitive relation on A, then we're going to prove that the inverse of R is also a transitive relation. So if you just want to take a couple minutes to think about this, then we'll go ahead and go through the solution. I'll give you about like 2 to 3 minutes. Think about it. All right, so let's go through the solution. Peter in chat definitely has, the right idea for how we can kind of do this proof. So first, we'll just let the transitive relation R on set A be given. And then when we start proving transitivity, we need 3 elements in the set A. So let's just let A, B, C be some 3 elements in the set A, and given such that for transitivity, you always assume that we have A is an element of B, and then B is an element, or BC, AB is an element of our relation, and BC is an element of relation, and then we just need to show that AC is in the relation. So we're going to have that AB is an element of the inverse, and BC is an element of the inverse relation. And then we need to somehow conclude that AC is an element of the inverse relation. So first, let's utilize the fact that we know that that AB is in the inverse relation. So that tells us that if AB is in the inverse, then BA must be an element of just the relation R, and CB is an element of R, just using property of the inverse. So then we were given that R was already a transitive relation. So we've got C is related to B, B is related to A, so C is related to A. So then CA is an element of R. And then it follows, using our inverse relation, that we must have had AC be an element of the inverse. So therefore, we've shown that R inverse is transitive. Any questions on this proof? No, don't see any. Awesome. Yeah, so just make sure that you're also able to prove properties about relations just in general, on general relations. So here we didn't know anything about the relation R or what the set A was, but we can still prove properties about transitivity. We can also do similar things for reflexivity and symmetry without knowing anything about the relation. So make sure that you're still kind of able to do these proofs in general for some unknown relations. So let's move on to the next problem. So we're going to do some on functions. So here we're determining whether or not the following function is one-to-one and onto. And then if the property doesn't hold, like the previous example we did earlier, we're not going to prove it. We're not going to prove if a property does hold, if it's one-to-one or onto. But if it's not true, you need to give a specific counterexample. So we're looking at the function from over the reals to the reals, with the rule that f of x is equal to x squared plus 4x plus 1. And then if you want to go ahead and write this down, I'm going to take a screenshot to post in chat, and then we'll go ahead and do breakout rooms for this one as well. So there's the file in chat if you need to download it. So you can go ahead and look when you're in your breakout room. And then let me go ahead and assign the breakout rooms. Okay, all right. Looks like everyone's back. So hopefully that was enough time to talk a little bit about this problem. So what I did is I just went ahead and did a very rough sketch here of what the function looks like in general. I think that's what makes it a little bit easier sometimes when we're talking about some of these functions to just easily see what properties apply. So if you just want to type in chat, let's do one-to-one first. Do you think this function is one-to-one or not? Yeah, so we have some people saying no, this function is not one-to-one. And that's correct. What one-to-one is actually is equivalent to is and what makes it really easy to see here with this x squared function is it's equivalent to what's called the horizontal line test. So you'll remember back from like high school, the vertical line test tells us whether or not something's a function as long as a vertical line passes through one and only one point. There's a similar thing for one-to-one in that if you can draw a horizontal line and it passes through 2 points, then you know the function's not one-to-one. But we need to be able to give a specific example to explain why this function's not one-to-one. And so one way we can do that is we can look at 2 points that are, since we're looking at x squared, we can look at points that are symmetric to each other. So we can look at what happens at f of -1, since our vertex is centered at -2, -3. And so if you look at f of -1, then this is going to equal to -2. And if we look at f of -3, that's also going to equal -2. So we have f of x1 and f of x2 that are equal, but -1 does not equal -3. So it's not one-to-one. We found 2 points where the outputs were the same, but the inputs were different. So we're not a one-to-one function. And then what about onto? Any ideas if you just want to type in chat whether or not you think the function is onto? Yeah, so you have a couple of people saying no, it's not onto, and that is correct. This is not an onto function. And in order to show that it's not onto, we need to find some point that this function does not map to in the codomain. So it's easy to see here with this graph that the lowest value we get in the codomain is -3. And the function doesn't map to any points below it. So we just need to pick one point, show that there's nothing that maps to it from the domain. So let's look at -4 and see if a value maps to -4. So to see what x value maps to -4, we would need to solve this equation. And then if you remember from, I don't know, like high school or something, middle school maybe, quadratic formula, and we can see what this value is. So x would be equal to -4 plus or minus the square root of 4 squared minus 4 times 1 times 5 all over 2 times 1. And then that would be -4 plus or minus the square root of, you have -4 there over 2. And this value is not in the reals. It's a complex number. So we showed that if there was a value that had to map to -4, it can have been in the reals. So thus, it is not onto. Okay, yeah, so someone has a question. If domain is equal to x and codomain is equal to y, does that mean that graphically you can tell that a function is onto if both ends go to infinity, negative infinity on the y-axis? Yes. Yes, with the caveat there that your codomain is the entire set of the reals. So then, yeah, so let me go to another page here. So yeah, if you have a function like this, and the arrows go this way, as long as they do, in fact, go down forever, and this one goes up forever, you can show that it's onto over the set of reals. Naturals is more tricky. For example, you can, like the function, let's look at the function. This is a really good question, by the way. This is, yeah. So if we look at this function, f of x is equal to x cubed, if we were looking at this, say, over the naturals, if we define f, say here, over the naturals to the naturals, this is not an onto function. Even though for that part of the graph, we'd be looking at, this portion of the graph, there's nothing from the naturals that would map to that. For example, 2, there nothing that would map to 2 from the naturals, because it would need to have been the cube root of 2. Would your input be? So yeah, so if we're looking at the reals, this is a good graphic way to see that. But over other domains and codomains, not necessarily. The other important thing to remember about onto is it's not necessarily, it's more a property about your codomain rather than a property about the function itself. So if we made the codomain of this function, if we had instead changed it to be our to be the set of all real numbers greater than or equal to -3, if that was our codomain, this would be an onto function. Because then our codomain is just restricted to the values that we have defined for our function. So make sure you remember that when you're looking at onto, you have to really be looking at what the domain and codomain are and how those interact in regards to the function in order to prove it. So it's not just you can look at a function like x squared, for example, and be like, oh, it's not onto. You really need to look at what exactly are domains and codomains. So yeah, really good question. Any other questions? Awesome. So let's go to the next problem. We've got about 6 minutes left, so we can get most of the way through this one. So here we're working on proving properties of functions. So here we've got the function f defined from the interval 1 to infinity. And it's the function with the rule that f of x is equal to x over x minus 1. And we need to prove that f is 1-to-1 and onto. And then we also need to find the inverse function of f, because we know that if a function is 1-to-1 and it is onto, then it's bijective, and then it has a well-defined inverse. So I'm just going to try to go through this one. For the onto case first, and we'll see if we have time for the 1-to-1 case. I want to go through the onto case because I know on the homework, some people got a little bit tripped up on proving onto for some of the functions. And so I just want to make sure we have a solid idea of how to prove onto. So when we're proving onto, we need to show that for all y in our codomain, that there exists an x from the domain such that f of x is equal to y. So when we start with onto, we want to just let y. So we're going to let y be some element, some arbitrary element of our codomain. And then we want to find what is the element x that maps to this element y from the domain. So what we have to do here is, so then we're going to try to find what x maps to this y. So if we let at y be equal to x over x minus 1, then we need to solve for x. So we can know what value would map to y. So if we solve this function, we'll if we multiply both sides by x minus 1, then we'll get yx minus y is equal to x. Yx minus x will be equal to y. Add y to both sides, subtract x from both sides. Then we're going to factor out an x here, so we'll have x times y minus 1 is equal to y. And if we solve for x, divide both sides by y over 1, we'll get x is equal to y over y minus 1. So this is the element x such that f of x maps to the element y. But we need to do something more. So we found the element that we think maps to this. But we need to show that this element x is actually in the domain. So it's actually in the range from 1 to infinity. So let's think about why this is in this interval. So we already had that y was in the interval from 1 to infinity. So we know that y is greater than or equal to 1. And then we also know something then about y minus 1. So then y minus 1, this is actually not greater than or equal to, it's strictly greater than, because we had open parentheses here. If this would have been brackets, we would have included 1, but open parentheses, we can say that's strictly greater than 1. So y minus 1 then is greater than 0. And we also have that y is greater than y minus 1. So what does this tell us? Well, this tells us that the numerator is positive, the denominator is positive, and the numerator is larger than the denominator. So thus, y over y minus 1 is also greater than 1. And so it's in the range from 1 to infinity. And it's well defined because we know that the denominator is strictly greater than 0, so it's impossible for us to divide by 0. So you know that this element had to have been in our domain. Any questions on this part for what we showed here? So we found the element x that maps to this, and then we needed to show that it's in the domain. Yeah, so x is an element from, oh yes, x. That needs to be x. So yeah, so x is an element in the range of 1 to infinity. Awesome. So then what we can do now is we found the element x. It's y over y minus 1. We can show that f of x actually does map to this. Does map to y. So what we can do is, well then, if we use this x, that is f of y over y minus 1, then we have, I'm just going to quickly wrap this up. I know we're a little bit over. And then if we do common denominator here, then we'll end up with y minus 1 over y minus 1. And that'll be equal to y over y minus 1 over y minus y. That's just 0. So end up with a positive 1 over y minus 1. Multiply top and bottom by y over y minus 1. And that'll just be equal to y. So thus, f of x is onto. We found an element x from the domain that maps onto this generic element y we found in the codomain. So it's an onto function. And then if we wanted to prove one-to-one for this function, that's fairly straightforward. You just let, if we wanted to do one-to-one, then we just let x1, x2 be an element in our domain such that f of x1 is f of x2. And then you just need to conclude by using algebra that x1 is equal to x2. Make sure you show these steps. Some of the homework just said, oh, we have f of x1 is equal to f of x2, and then x1 is equal to x2. So we actually need to show the steps algebraically in order to conclude that. So make sure you're showing your work on the quiz on Tuesday for each of these steps. So any last minute questions before we go ahead and end the discussion? No, it doesn't look like it. Awesome. Well, don't forget that your quiz is on next Tuesday. So good luck on that. And then hope you all have a good rest of your day.